Hi, my name is Lindsay Hoffman. Today we are going to be discussing vapor-liquid equilibrium in 5 different parts. For this first part, we are going to begin by talking about bubble point and dew pressure. More specifically, we're going to be deriving equations that can be solved for the dew temperature, dew pressure, bubble temperature, and bubble pressure for an ideal mixture of n components that follows Reynolds' law. So we haven't really discussed Reynolds' law yet, but it is given that Xi is going to be our mole fraction of our component in the liquid phase multiplied by our Pi sat, which is going to be the pure saturation in the vapor phase. And that's going to be equal to the mole fraction of that component in the vapor phase times the total pressure. So the right-hand side of Reynolds' law is simply the partial pressure for a given compound, because you have the mole fraction times the total pressure. That gives us partial pressure for a given compound. And if you can see on the right here, I have the Antoine equation written. We are going to be using that to come up with our equations. If you remember before, we used the Antoine equation to come up with a vapor-liquid equilibrium curve for pure substance. And we're going to be using this, especially looking at bubble temperature and dew temperature, because we're going to be able to calculate that saturation vapor pressure to then find those temperatures that we're going to need. So we're going to start by looking at bubble pressure. Bubble pressure is basically the pressure at which the first bubble of gas is formed at a given temperature for a liquid mixture. So to put that in simpler terms, it's basically the pressure that the liquid becomes warm enough to form its first bubble, like before boiling. So to come up with the equation for this, I have drawn up a diagram here, and this is going to have all the information we're going to need to come up with an equation. So we have a purely liquid substance inside of our tank here with a piston above. So we just have liquid in there. Our external pressure is going to be 1 atmosphere. And here below we have 30% benzene and 70% toluene ratio for our purely liquid mixture. So that information is basically going to give us the mole fraction for a liquid phase, which is the Xi that we see over here in Reynolds' law. And lastly, we are given an external temperature of 373 degrees Kelvin, and we can actually use that temperature in our Antoine equation to find the pure saturation vapor pressure. And then that's going to be the same over here. So looking at Raoult's law, we have the entirety of the left-hand side of the equation. And the right-hand side of the equation is just partial pressure. And if you remember from basic chemistry, the total pressure is equal to the sum of the partial pressures. So we can simplify with some substitution that the bubble pressure is going to be equal to the sum of our mole fraction component in the liquid phase, Xi, times our saturation pressure in the vapor phase. So that's going to be our bubble pressure equation. I'll just rewrite that down here. Simple enough. So before we move forward, I wanted to kind of explain bubble pressure a little more. If you were to try and find bubble pressure in a practical sense, you could do that. So for example, if we have our temperature set at 373 Kelvin, that's below the boiling point of benzene, which is our more volatile of the two components. So we wouldn't see any vapor bubbles at this resting system currently. But if we were to pull up on that piston to decrease the pressure inside of our system and make it so that pressure, the internal pressure is equal to the external pressure, we would begin to form that first vapor bubble. But as this is going to happen, if you can imagine, the temperature inside is going to decrease because there's work being done internally to the external. So that's going to give an internal energy decrease. So to determine what pressure those bubbles are actually forming at, heat would need to be supplied to our system so that we keep that constant temperature at 373 Kelvin. But then while that first bubble is going to form when internal pressure is equal to the external pressure, that bubble is going to have a different composition of benzene to toluene. So we're going to have 30% benzene, 70% toluene in the liquid, but the vapor is going to have a different percent composition of each component. So now let's take a look at bubble temperature. We're going to use our equation from bubble pressure to come up with this. So looking at that up here, let's see, so we'll have our pressure, which we're given our total pressure, so we know that information. And then we also still know our mole fraction in the liquid phase. But the thing we don't know is our temperature. That's what we're trying to find. And temperature is needed to calculate our saturation pressure in the vapor phase. So we could easily do some substitution to be able to solve for our temperature from our Antoine equation up above. So I will write that out now. And then if you were to write out the sum for each component, we would have two components because we have two components in our mixture over here. It would be quite rigorous to try and calculate the temperature by hand. Could be done, but we're just going to be doing that later in Python because that'll be a little bit easier for us. So now we're going to move on to do temperature and do pressure. So do pressure is going to be the pressure at which the first drop of liquid is going to form from a mixture of gases at a given temperature. So if we look back over at our diagram over here, I'm going to change this to 400 Kelvin because at this temperature, this is going to be higher than the boiling point of our least volatile component. So that's going to be toluene. And that's just so we have a purely gases mixture. So if we were to push down on this piston, we're going to be increasing the internal pressure. And since we are going to be exerting work onto the system by pushing that down, we need to have some kind of cooling jacket as we compress to keep the temperature constant. And that first drop of liquid is going to have some mole fraction of benzene and some mole fraction of toluene. A very important thing to note is that the sum of these mole fractions is going to be equal to 1. And that might seem like an obvious statement, but it's going to be extremely useful in coming up with our equations for due pressure and due temperature. So again, we're going to still be using Raoult's law to come up with our equation. Because the sum of our mole fraction is equal to 1 when the first drop of liquid is going to be formed, we are going to want to solve Raoult's law for the mole fraction in the liquid phase, which is for our xi component. So if we were to rewrite this, it would give us xi, the mole fraction in the liquid phase, is equal to the mole fraction in the vapor phase times the total pressure divided by our pure saturation pressure of a vapor. So I'll go ahead and write that out for us. Equals going to be yi over saturation pressure and okay. So because we have two components of our mole fractions, we're going to want to sum each side. So that way we just account for all of those, or both of those. And again, it's going to be equal to 1. So looking at our equation here, we know yi, the mole fraction in the vapor phase. We know temperature, so we can calculate the saturation pressure of vapor. And we want to find our pressure. I left out pressure. Yep. So this should be yi times our pressure. Sorry. So that's what we want to find. So we can pull out that P and divide so we can set everything equal to our total pressure. So that's going to give us the sum of our yi. I'm sorry. We want to pull out the P and then we need to do 1 over our sum of our mole fraction in the vapor phase over our saturated pressure in the vapor phase. So that's going to be our expression for due pressure. So now moving on to due temperature. Just like with our bubble pressure above, we used that bubble pressure expression to find our bubble temperature. We're going to be doing that again, the due pressure and temperature. So looking at our due pressure expression in terms of due temperature, we know our pressure this time, and we still know our mole fraction in the vapor phase. But again, we don't know our saturation pressure. So, and that's because we don't know temperature. So again, we're just going to be doing a substitution. So we'll have 1 over our summation of 1 y over 10 to the a minus b over c plus t. That's in the exponent. I'll rewrite that so you can tell. And again, that's a very complicated algebraic expression to solve for t. If you wanted to write that out and solve for t, you could, but we're going to be doing it in Python because it's much simpler. So hopefully this was a good start and gives you some more knowledge of liquid vapor equilibrium with bubble pressure, temperature, due temperature, before we begin to expand on this knowledge.